We're now going to have a look at the concept entitled thermal equilibrium. And we have come across this concept in grade 8 of your physics studies. Now, let's imagine we have two bodies, two substances, and these two substances or two bodies, they have different temperatures. Now, let's imagine that we then take these two bodies or these two substances and we place them close together. Now, what will happen is that thermal energy will be transmitted or will be transferred from one of the bodies to the other. So let's say we have a body or a substance, and let's call that substance A. And let's say we have another substance, and we're going to call that substance B. And let's say that the initial temperature of substance A is 50 degrees Celsius, and the initial temperature of substance B is 10 degrees Celsius. Now, what will happen is that after a period of time, thermal equilibrium will be established. And I'll explain what that is in a moment. But the final temperature after a period of time will be 25 degrees Celsius for substance or body A and 25 degrees Celsius for body B. In other words, they will acquire the same temperature. So the direct flow of thermal energy will be from the body which has the highest temperature to the body which has the lowest temperature. And once these two bodies are of the same temperature, there won't be any flow of thermal energy from one to the other. And when that happens, when there's no net flow of thermal energy, we say that the bodies are in thermal equilibrium. Now, heat energy flows from a hotter body to a colder body, and that's something that we've established, and many of you should know this. And the heat will flow from the hotter body in terms of thermal energy to the colder body, and it will continue flowing until the two bodies acquire the same temperature. Now, when these two bodies have the same temperature, as we saw in the previous example, then what will happen is that the flow of thermal energy will stop. And when this happens, we have what's known as thermal equilibrium. Now, this is important because it brings us very nicely to one of the laws of thermodynamics. And the zeroth law of thermodynamics, which is just one of many laws that you may come across when you study thermodynamics in physics, this law, the zeroth law, it basically states the following. If two thermodynamic systems are each in thermal equilibrium with a third body or a third system, then those two thermodynamic systems, they're going to be in thermal equilibrium with each other. In other words, if we have two substances, A and B, and we then attach them to either end of a third substance, C, which is in the middle of A and B, if each of those, A and B, are in thermal equilibrium with C, then A and B are in thermal equilibrium with each other. That's what that rule or that law is basically saying. So we can say that two physical systems, two substances, are in thermal equilibrium if there is no net flow of thermal energy between them, when they're connected by a path which is permeable to heat. That means they're connected by a path which allows heat to actually transfer through it. So, for example, here we have one system at a temperature of 100 degrees Celsius. here we have another system at 50 degrees Celsius, and you can see that the substance at 100 degrees Celsius is actually allowing thermal energy to flow to the other substance, which is at 50 degrees Celsius. So there's a permeable pathway which allows the thermal energy to flow from the substance at a temperature of 100 degrees to that other substance of a temperature of 50 degrees Celsius. And so when thermal equilibrium is reached, then the temperature of the two substances is going to be 75 degrees Celsius. They're going to be identical. So thermal equilibrium obeys the zeroth law of thermodynamics that we saw previously. The first law of thermodynamics states the following. This is the law of conservation of energy, and it basically states that energy is neither created nor destroyed. In other words, you cannot create energy and you cannot destroy it. Energy is only transferred from one form to another. The second law of thermodynamics, well, this basically implies the following. That heat or thermal energy can't flow from a cold body to a hotter body in nature. So you never actually get a flow of thermal energy from a cold substance to a hot substance. It's always the other way around. The flow or the transfer of thermal energy is always from the hotter body to the cooler body. The second law of thermodynamics also implies that processes can be irreversible. Now, the increase in internal energy of a system, well, that is equal to the sum of the thermal energy or the heat energy gained and the work done on the system. So in other words, we're talking about work done on the system plus the heat energy gained by that system. And again, we're going to explore this in a bit more detail when we look at the laws of thermodynamics. Now, the third law of thermodynamics, this states the following. When the temperature of the system approaches to absolute zero, and by absolute zero, you should be able to recall that we are talking about a temperature of negative 273.15 degrees. So when the temperature of a system approaches that particular temperature, what happens is that the entropy, now when we talk about entropy, we're really just talking about the randomness of the system. And this is something that you probably will touch on a bit later on in your physics when you get into, say, year 12. But the important thing is to know that when we talk about entropy, we're talking about the randomness of the system. So at a temperature of absolute zero, the entropy of a system will decrease. And when we talk about entropy, we're really also talking about disorder. The more disordered the system is, the greater the entropy. So when the entropy of the system decreases, we mean that it becomes less disordered. So at minus 273.15 degrees Celsius, essentially what we're saying is that in a system, everything literally comes to a standstill. In other words, everything stops. Entropy decreases. There's less randomness. There's less movement. Now, in reality, the entropy of a system will not be decreased. And the reason being is because the universe is expanding. And again, this might seem a little bit complicated, but really because the universe is not finite. That means it's constantly moving, it's constantly expanding, it's constantly getting bigger and bigger. It means in reality we will never really have an entropy which decreases to zero. So in a way, we're talking about the effects of temperature on the entropy of a system. And at absolute zero, the entropy, in theory, decreases. But don't worry too much about the third law of thermodynamics at this stage in year 9. It's something that you will look into in a lot more detail when you get into year 12. Now we're going to have a look at the expansion of solids, liquids, and gases, and this is less complicated than the third law of thermodynamics. Basically, what we are looking at when we study the expansion of solids, liquids, and gases is that in thermal expansion, we're looking at the tendency of matter to change its length, maybe its area, maybe its volume, as a result of change in temperature. And that's what we mean by thermal expansion. The change in temperature and the effect of that change in temperature on the length, area, or volume of matter. This is one of the important factors which is used in thermometers, as we mentioned earlier on. So in terms of what we mean by thermal expansion, then well, we can say that thermal expansion is defined as the change in the dimension of a body as a result of a change in temperature. There are 3 types of thermal expansion, and we're going to explore these 3 types in some detail. There is linear expansion. There is area expansion. There is volume expansion. When we talk about expansions in solids, then we really are talking about all 3 of these. So in a solid, of these 3 types of thermal expansions can take place. So in other words, in a solid, you can get the solid material actually expanding in a linear manner. You can get the area of the material expanding, and you can get the volume of the material expanding. When we consider a liquid, the only real type of expansion that occurs is what's called a volume expansion. When we talk about gases, then gases tend to expand greater than liquids and solids at the same temperature. If we have a solid, a liquid, and a gas at the same temperature, then the gas will expand to a greater degree than the liquid or the solid. We've talked a bit about expansion. And we've said that expansion occurs when a substance is exposed to thermal energy or heat energy, which causes the substance to actually expand. And in this diagram on the right-hand side, you can see what we have in terms of a bimetallic strip. In other words, what we have here is a strip which consists of 2 different types of metals which are connected to each other. And what happens is that as you apply heat to this bimetallic strip, it actually begins to expand, and as a result of the expansion, you can see that the strip itself begins to move away from its original position, which is a horizontal position. And in fact, it is this deflection or movement away from the horizontal position that we're actually interested in, because that degree of deflection, that movement from this position to, for example, this position, the bending of the bimetallic strip, is actually indirectly related to the temperature. So you can actually use bimetallic strips as an indirect measure of the thermal energy or the heat, and as a result of that, the temperature. Now, there is a mathematical expression which relates the length of the strip in terms of the change in length of the strip to its initial length, and something that we call an expansion coefficient. So if we look at this mathematical expression, we can see that the change in length of the bimetallic strip when it's experiencing thermal energy or heat energy is equal to its initial length, that is the length of the strip before it was exposed to this thermal energy, multiplied by the linear expansion coefficient, and then brackets multiplied by the change in temperature. So we can use this equation to determine the change in the length of the strip. So let's have a look at an example where we actually do that. A copper rod with an initial length of 0.5 meters is heated from 15 degrees Celsius to 95 degrees Celsius. If its linear expansion coefficient is 1.65 times 10 to the minus 5 per degree Celsius, what will be its increased length? So in other words, the question is asking you, how much does the actual metal, or the rod, in this case the copper rod, how much does it actually increase in length when it's heated from 15 degrees Celsius to 95 degrees Celsius? So let's have a look now at the solution to this. So we're going to apply this equation, that is, the change in length is equal to the initial length multiplied by the linear expansion coefficient, which is then multiplied by the temperature change. And if we substitute in the value for the length, which is 0.5 meters, and we multiply that by the linear expansion coefficient, which is 1.65 times 10 to the minus 5, and then we multiply that again by the change in temperature, we would get a value for the change in length, which is equal to 6.6 times 10 to the minus 4 meters. So you should be able to see that the change in length is actually relatively small compared to the initial length. But despite that, that is still a significant change in length. In fact, it indicates that the metal itself does expand when it's exposed to thermal energy. Let's have a look now at another question. Let's suppose that we cut out a circular piece from a rectangular plate as shown in this diagram here. So in the middle of this rectangular piece, we have managed to cut out a perfect circle from that particular piece. Now, which one of the processes given below can help us in passing the rectangular piece that we've just cut out through the hole? Now, is it by increasing the temperature of the rectangular plate and the circular piece? Is it by decreasing the temperature of the circular piece? And finally, C, is it by decreasing the temperature of the rectangular plate and the circular piece? Well, if you look at the solution to this, you'll see that all of these options do in fact help us in passing the circular piece through the hole, because by increasing the temperature of the rectangular plate and the circular piece, then you're increasing the expansion of both of those, and you will increase the expansion in the same proportion so that they will still be able to fit the circular piece through the hole. And similarly, if you decrease the temperature of the circular piece, then that will obviously become smaller, and it will then fit through the hole in the rectangular plate. And if you decrease the temperature of the rectangular plate and the circular piece, then they will decrease relative to each other at the same rate. And so as a result of that, the circular piece will fit through the hole in the rectangular plate. Now we've seen that there are in fact various phases or transition between various phases. For example, if we go from a solid to a liquid, that is classified as the melting phase. If we go from a liquid to a gas, that is regarded as the boiling phase. And if we go from a liquid to a solid, that's referred to as the solidifying phase. And finally, from a gas to a liquid, that's regarded to be the condensation phase. So in other words, as you go from one phase to another, there is actually a change in the structure of the substances as they move from one phase to another. Now, you can actually calculate the amount of energy involved in going from, for example, a solid to a liquid, and from a liquid to a gas, and from a liquid to a solid, and from a gas to a liquid. And it's important to know that when we talk about the melting phase, that when you apply, for example, thermal energy to ice, for example, in order to melt ice, for ice to go from the solid phase to the liquid phase, you will not see an increase in temperature during the melting phase. In other words, the increase in temperature only occurs after all of the solid has melted and turned into the liquid. And so that particular phase where you have a solid turning into a liquid, the amount of energy required to totally break all the intermolecular forces in the solid so that it becomes a liquid can be calculated using this expression here, where Q is the amount of energy required to, for example, change one phase or state to another state, solid to a liquid, liquid to a gas, liquid to a solid, or gas to a liquid. And that thermal energy that's required is equal to the mass of the substance and multiplied by L. And L has a special particular name in physics. It's the latent heat. And we're going to explore this in a bit more detail. Now, we can use a number of techniques or methods to calculate energies involving specific latent heat. And we've come across this in the previous slide, that the specific latent heat, L, is actually defined as this equation here. So we can say that Q is equal to M times the specific latent heat. So the specific latent heat really is just Q divided by M, which is the amount of thermal energy required to convert a substance from one state to another state divided by its mass. So let's have a look at some examples here. Bob has designed a 525 kilogram ice chair. How much heat must he remove from water at 0 degrees Celsius to make the ice chair? And also in this particular case, the ice chair is also at 0 degrees Celsius. So in the photograph at the side here, you can see this is his ice chair. And what the question is asking is, how much heat must Bob remove from water at 0 degrees Celsius in order to make the ice chair also at 0 degrees Celsius? So let's have a look at this, because it's quite an important example in terms of getting you to understand the phase change involved and the amount of thermal energy required during a phase change. Now, in a phase change, if the change in temperature is equal to 0, we can use this expression here. So we're using Q is equal to M times L, because there's no change in temperature during the phase change. And that's important because when a solid, for example, melts, or when, for example, water begins to boil, as I mentioned previously, the temperature, which is measured using your thermometer, does not change during that phase. It's as if the temperature has just stood still and has not changed whatsoever. And this is because in a phase change, before the temperature can actually change, all of the particles, for example, in a solid which is undergoing melting, all of the particles must undergo melting. So the intermolecular forces holding all of the particles in a solid, all of them have to be broken before you can get the phase change from solid to liquid. And during that period, there isn't a temperature rise. So we tend to use this expression during phase changes. Now, because the phase change is one of freezing, in other words, we're going from a liquid water to ice. Remember, Bobby's designing his chair, ice chair, and he's actually removing heat from water in order for the water to then become ice. In other words, it's freezing water. So because the phase change is freezing, we are going to use from the data the latent heat of freezing. And we can get that from the data booklet. So, for example, for a water to ice phase, in order to get water to change into ice, we can use the latent heat, and that's going to be 3.33 times 10 to the 5 joules per kilogram to the -1. And so what we do is we use this example in terms of the calculation equation, and we say thus Q is equal to the mass. In this case, the mass is 525 kilograms multiplied by the latent or the specific latent heat for freezing, which is 3.33 times 10 to the power of 5, and that will give you an answer of 175 times 10 to the 6 joules. In other words, in order for the water to freeze totally to ice, you would need to remove this amount of heat from the water in order to freeze 525 kilograms of water.